Determining the shape of a new part is challenging. Many times, designers start new designs simply based on existing designs. They might take a part and try to remove or add material simply by tweaking the existing features and dimensions. This means that newer design concepts are never considered, and modifying an existing part might actually create an over-designed part for a particular application. But trying to think of a completely new part design takes time. Where do you even begin? Experience helps, but intuition doesn't necessarily create the best part either. If the development schedule is tight, do you have the time for a long trial and error process of creating a part, then simulating it to see if it works? Why not start with simulation instead? One of the ways to achieve simulation-driven design is with topology optimization. With topology optimization, you don't begin with a design at all. Instead, a designer within NXCAD models the design space, meaning the package space that the design would ultimately live in, and simulates it based on expected loading conditions. The result is a completely new conceptualized part geometry that meets structural performance requirements immediately, yet is lighter than the existing design. If you've never seen topology optimization before, this next demonstration will help to give you a better understanding of what it is and how it works. A business jet developer is looking for ways to reduce weight of an aircraft that's currently under development, and they feel that the elevator bell crank could be just one of the components ready for a redesign. The elevator bell crank is a critical mechanical component that connects the actuation from the pilot's joystick directly to the elevators that control pitch, and you can see the original design here. But instead of using a designer's imagination for the redesign, they decide to use topology optimization to suggest a new potential design. To do this, the designer first starts with a model of the design space, meaning the area that the crank could fit within. In this case, the gray area is the design space, and only half of the design space is modeled since it's a symmetric part. The red area represents an area where we don't want the material to be placed for the design. The designer picks the topology optimization solution from the NX interface and follows the simple commands in the menu that are laid out in the steps of the process. The designer first identifies the design space, symmetry plane, and material for the design space. The designer also notes that there are pin connections within the design space, which the optimizer will then maintain as it determines the part shape. The designer also identifies the red areas as the keep-out zones. Next, the designer defines loads that the part will experience at the pin connections. The final step before running the solution is to set up the optimization targets, which is set to 0.17 kilograms for this part. The topology optimization run is then submitted, and it takes some time for it to run through all of the iterations, which we've edited out here in this demo in the interest of time. Once the optimization is complete, the results of the new shape are created in the form of facet data, which we can then open in NX. You can see the new part here in blue. If we isolate the part and its design space, you can get a better feel for the new part shape and how it's radically different from the original shape. Traditional CAD tools can't do precise design operations on facet models like this one. You would actually need to completely remodel this part in CAD using the facet model as a guide in order to get usable geometry that you can then refine. This slows down innovation. But with NXCAD, even though this part is in the form of facet data, we can continue to refine this shape by using Convergent Modeling. In this example, the designer sees a need to beef up the material around the short connecting strands on each side of the part. So the designer decides to use the Realize Shape commands within NX to begin working to reshape the geometry here. The designer first begins by defining a tube cage around the section to be modified. With the cage in place, the designer transforms the shape by simply pulling and pushing the different vertices and faces of the cage to get a more desirable shape. Once the designer has the desired shape, the designer then can apply this to the other side of the part by defining a symmetry plane. Any further operations automatically get applied to both sides. Once complete, the designer unites the geometry with the part to create the final shape. Would you have been able to imagine this final shape on your own without simulation?